started. Well, it's my very great pleasure to introduce Steve Blackburn, who has been a collaborator, a colleague, and a very good friend for many, many years. I'm not sure we'll count them at this point. Steve is probably the preeminent expert on garbage collection in the world these days. I'd say that he's probably delivered most of the interesting results over the last 25 years or so. Greatest hits include things like MMTk, which was originally written as part of Jike's RVM, a lot of work that he did inside of Jike's and Java. Da Capo, yet another of the greatest hits. And his recent work looking at bringing reference counting back into sort of competitive space for high-performance garbage collection. So Steve's going to tell us today about MMTk. This is MMTk Mark II, so it's not the original version. It was written for Jike's RVM, but is indeed something that is hopefully available to all of you to use if you're so inclined. So welcome, Steve.
Thanks, Tony. Thank you, everyone. It's great to see you here, and it's a special thank you to the organizers, the student volunteers, and our guest chair, and everyone who traveled more than a little while to get here, because it's I know what it's like to travel a long way for a conference. So thank you. I'm hoping this will be fun. Okay, so if you have questions or you want to interject, feel free to jump in if you have a question. Some of this may be a bit controversial. I'm hoping you'll find this interesting, and I'm going to stick my neck out a little way in making some of the claims I'm going to make here, but I do have the data to back it up. So I'm happy to engage in a discussion about this. But let's get started. I'm going to talk about MMTk. As Tony said, MMTk goes back a while. I'll talk a little bit about the history of that in a few moments. And I'm going to talk about modular VM development. And these are things I'm pretty passionate about. Okay, so I'm going to claim that we've got a big problem in garbage collection. And some of you might look at that and say, okay, Steve, you're being a little dramatic. But I don't think so. I think that we actually have a serious problem, a really serious problem in GC at the moment. And I'm going to talk about that in more detail now. So that's the premise. We've got a problem, and let's have a look at it. I'm going to start off by asking the question, how much does GC cost? How much does GC cost? And most of us will hope that GC, the rule of thumb is, it costs 10%, something like that, right? That's the rule of thumb that many of us might operate off of in a high performance setting. But I think it's actually really unclear. Well, I know it's really unclear. It's really unclear how much GC costs. There's a lot of reasons for this, and I think that in itself is a big problem. And I'm going to start off by talking about some work that we recently published with my student who's just stepped out of the room right on cue. Zusian, who was sitting in the back there earlier. Zusian Kai was the lead on this piece of work, and it gets to the heart of the question about how much GC costs and what we know about the meta question about what we know about how much GC costs. So the first question is GC really a solved problem? Some people say, okay, GC is pretty ho-hum. We know how to do GC. It's all done. Okay, done and dusted. There's not much to see here, but I'm not sure that's so clear, and I think the first thing you need to do, as I said before, is need to look at how much it's really costing us. So if we were to consider three very silly hypothetical collectors, which I've got illustrated here on the screen, consider them and say, okay, how much do they cost? One way you could do it is just run your favorite benchmark or benchmark suites and measure the total time for each of them and say, okay, so the one at the bottom costs more than the one at the top there, okay? Yep.
So you're looking at the one-dimensional metric, which is just the execution time, right?
No, I'm not. No, I'll get to that. This is very much a multi-dimensional thing. I'm absolutely not looking at just the execution time, and you'll see in a minute.
Okay.
And in fact, I'm pointing to that as being one of the problems, right? And here's Zusian right here, whose work I'm talking about. All right, so let's start by considering three very, very silly and simple collectors. The first one is a classic collector like Semispace, which people would not normally use in a production setting these days for a variety of fairly obvious reasons, including large overheads. And the other one is a classic generational collector, which is very widely used in production settings. And then the last one is what we call no GC or epsilon in OpenJDK. And that there is a collector which doesn't collect, which is often used as a baseline to help us understand what the overheads in a collector really are. And the idea is that all it does is allocate, okay? So they're the three collectors, and you might run them against your benchmark and say, oh, okay, clear enough, no GC is the winner here, and generational is somewhat better than the other. Okay, that's a hopelessly naive view, and that's not what we're going to do here. What we really want to understand is, I think what we really want to understand is, if we could know what this program would perform like if the GC were magical and did everything for free, what would the program performance be like, and how much overhead are these adding with respect to that baseline? I think that's at the heart of what we really want to know. And of course, the magical GC doesn't exist by definition, so we have a little bit of a problem. But that's where we're aiming at, okay? And what Zosian's work does here is it picks apart that and arrives at something pretty close to the magical GC, methodologically. Okay, so if we've got these simple GCs, one thing we can do for sure, and we have been doing for a long time, is look at discrete chunks of time in, for example, a single-threaded program with a single-threaded garbage collector and say, oh, the program stopped, the garbage collector's begun, stop the clock, start the GC clock, and so forth. And we can extract out those costs quite easily enough if that's what's happening, okay? And so we can see in this illustration here, the golden bits are the parts where the garbage collector is running, and the blue bits are when the application is running, okay? And you could use this to sort of say, well, the GC overheads are thus. However, that's far too simplistic, okay? That's far too simplistic, and of course, it's also monodimensional at this point. So if you look, I just changed the color of that blue, if you were watching carefully, the blue changed, because in fact there's bleed. There's not really this discrete yellow and blue. There's actually this murkiness where the GC actually imposes costs upon the mutator that you can't simply measure by starting and stopping a clock. And these include things like read and write barriers, the actual allocation sequence in the way it's formulated, and things, indirect costs, like effects on scheduling and effects on locality. Okay, so, yep, Jeremy.
There can't be any being bottom one, can there?
There absolutely can be, and I just the last words I spoke are the big clue. Can anyone else want to have a stab at what the costs are? Well, when I say GC, let's just spread it slightly broader to memory manager. There is a memory manager at work there. It's a very naive one, and it does have a cost. It's got to allocate the memory, and in particular for the no GC one, it has to manage where that memory is, and it's terrible at it because it doesn't collect. So it's got very poor locality. So it's got real costs in the TLB. Okay, we're going to see that in a minute. And so using that as your baseline is actually a really bad idea, because it is not a free magical GC at all. It's actually a somewhat costly GC, albeit less costly than some others. So as I said, some costs are very hard to separate from the application, such as allocation and barriers and indirect costs such as locality. All right. And if you've got concurrent GC, you've also got things happening in the background, which not only consume CPU cycles, but also may perturb caches and whatnot. Okay, so there are lots of things that you can't simply measure by starting and stopping a stopwatch. Okay, that's not adequate for this, right? And starting and stopping a stopwatch is more or less the state of the art in GC evaluation before this work. So, as I hinted before, it'd be really nice if we had this ideal application cost, where the ideal application was running with a magical perfect GC, which had no costs and did all the locality stuff that a really good GC would do. Okay, and then we could say, okay, let's compare these things against that. Now, as I said, we can't get this because we don't have the magical GC, so we have a little bit of a conundrum. So what can we do? Well, what we can do is we can approximate it, and the technique that we use for doing that, this is what Zosian's work was developed, is what we call distillation. So what we're going to do is we're going to distill out the best effort we can at what the GC costs are and take them away. Okay, imperfect, but better than nothing. Okay, so, and if we do this across multiple garbage collectors and multiple applications, we can get closer and closer to approximating that ideal cost. So we can pull out these discrete costs, like I just showed you there. Notice how in my little cartoon example here, Jeremy, that the simple collector is has a lower cost than the no GC. And that's exactly to the point I was making before. That is, there is actually a cost in the no GC, and I try to illustrate, or Zosian tried to illustrate in this cartoon here. Yeah.
So I was thinking, in order to figure out the ideal application cost, is it possible if we allocate more memory and then prevent GC from operating it because it won't get triggered because we have enough memory.
Sure, and that's what the NoGC is essentially doing. You just have a huge amount of physical memory, but as I said before, you have other costs. You've still got to allocate that memory somehow. You've got a allocation sequence, which is at the very least is going to bump a pointer, but you've also got these other costs like the TLB cost. If you don't collect it all, you get a very fragmented memory, and you actually really do pay for it. And this cartoon example here tries to illustrate that a little bit. There is a cost there. So this is what we call the distilled cost. These blue bars are what we call the distilled cost. And so what we're going to do is we're going to run a whole lot of garbage collectors for each benchmark. And better still, if we can, we're going to run them on multiple heap sizes. And we're going to say, what was the best result we ever saw? And we'll say, that's our best approximation to the ideal. Yep, Jeremy?
Hope you don't mind these interruptions, Steve. Would you consider, if you had it, a manually memory managed version of your benchmark as well?
Yes, I would. And interestingly enough, we've got a paper on something very close to that as well, which you can find on my webpage. I only put it up there about 3 or 4 days ago, so you probably haven't seen it. But at MPLR, we've done a whole lot of work with trying to understand the relationship between manual memory management and GC. And one of the ways we've done that is imposed manual memory management underneath the GC VM.
Connecting to that, do you also consider how much extra memory you need to have the GC?
Not in this analysis right here, but we'll get there in a moment. Okay, so far we're just abstracting over that, but we're going to get to that because there's obviously there's a big trade-off space going on here. So at the moment we're just imagining, we're just going to ignore that for the minute. Okay, but you can see already implicitly we're taking into account at least a little bit because you see the NoGC is paying because of its TLB costs, for example, just for example. Okay, so I'll just repeat what I was saying there. What we really want is this ideal cost. We can't possibly get that by definition because it relies on this magical GC that doesn't exist. But what we can do is look at multiple garbage collectors, pull out their explicitly exposed costs, find out what the mutated costs are, and then find the smallest for each benchmark and say the smallest one that we can find is still an upper bound on the ideal cost. Okay, so we're always going to have an upper bound on the ideal cost. And we're approaching that ideal cost as we use more GCs that have fewer and fewer implicit costs. Okay, so click. All right, so what I've illustrated here is the minimum distilled cost. That's the smallest one that we found. And then what we can do is we can subtract away the minimum distilled cost from the total cost and say that this is the lower bound overhead of the of this collector. This is what we call the LBO, lower bound overhead. Because the minimum distilled cost is an upper bound on the ideal GC, the difference is a lower bound on the cost. So when you see that red thing, it's costing you at least this much. Okay, it's a lower bound. It's costing you at least as much as what you see in that red bar. Okay, so everyone with me so far? We've developed a methodology here which allows us to put a lower bound on what the cost of your GC really is. Okay, this is really sluggish. Okay, so one of the nice things about it is that this approach is, and to your point about metrics, it's language and metric agnostic. So we can apply elbow like I just did in this cartoon example with respect to the war clock time, but you could also do it in terms of cache misses, energy, whatever metric you might have at hand. You can apply the same approach. So take your thing, work out what the lowest costing the baseline is for you with respect to that metric, whether it be energy or whatever, and then do this analysis. Okay, and we actually do that, and we'll demonstrate some results in a moment, which do that, and it exposes something interesting. And it's also language agnostic, so you can apply this in principle to any language runtime. Okay, so you can deploy this approach, this elbow approach, with respect to any of your VMs, in principle at least. All right, and I want to emphasize this is not the same as just comparing against the shortest running thing you've got, because as you can see in the graph there, even something like NoGC has a real cost associated with it. And interestingly enough, that cost, and not surprisingly perhaps, the lowest costing collector varies from benchmark to benchmark. So as you change your benchmark, you'll find a different collector has the lowest cost because of the nature of the benchmark. So in this benchmark here, Semispace may have the lowest cost, and this one over here, it may be the generational collector has the lowest cost, and then this one here, maybe NoGC does. But one thing that's interesting is NoGC was often not the lowest cost, or very often not the lowest cost. Okay, so here's some results. All right, and then this gets to your other question. One of you was asking about the time-space trade-off. Well, as GC people, we always want to think about GC as a time-space trade-off because that's fundamentally what it is. So we like to plot our data like this, which is to put on the x-axis the heap size, and on the y-axis the overhead. So what we've done here is this is the aggregate across a whole lot of the new decouple benchmarks. This is the new. This is as of a year ago, a snapshot from a year ago. A whole lot of the decouple benchmarks taking the average cost with respect to multiple heap sizes, where each benchmark is run at a multiple of the minimum heap size in which that particular benchmark could run. So for some benchmarks, that's a very small number, like a few tens of megabytes, and for other benchmarks, it's in the order of a gigabyte. So, but each one is expressed in terms of the multiple of the minimum in which benchmark could run. And then we see these curves, and what we're showing here, and Zussian did his analysis with respect to all of the current available production collectors in OpenJDK 17 as of November last year. Okay, so what you see here is 3 of them. I'm going to show you the others in a moment. What you see is 3 of them, and we see the serial collector, which is the oldest of these collectors, and the serial collector is a generational collector that only runs a single GC thread. So at GC time, it's a single thread, and so obviously that has real limitations on a multi-core machine, but it has other advantages. Parallel is very similar to serial, but it has a parallel collector. So when the GC happens, it'll run lots of GCs. And G1 is the garbage first collector, which was published in, I think, in 2006, and became available about 5 years after that, and became the default many years after that. So it took a long time from when conception to when it was actually deployed as a default garbage collector. But G1 makes different trade-offs. And what you see here is the different trade-offs between these collectors. And what you see is once you go lower than about 2.5x the smallest heap size, the time-space trade-off really kicks in. Conversely, as you get beyond about 4, things are converging on an asymptote, which is in the ballpark of 8 to 4%, 4 for the parallel and about 8 for the serial. Okay. Remember, this is with respect to the baseline of the lowest cost GC we have. And it's interesting because I'm going to show another result at the end of this talk, which has a different set of GCs. One thing that's notable is among the GCs that Zussian had available, which was the production GCs for OpenJDK 17, none of them were whole heap collectors without a barrier. That is, he had a no GC collector and all the other ones had barriers. So I think that what we'll see later on when we see some other results that Wen Yu, who's sitting right next to Zussian, did, the overhead actually is higher than what you're seeing here. And that's because the barrier costs become exposed once you introduce into your elbow analysis collectors which don't have barriers, which we don't have here except the no GC, which has its TLB problem. All right, so now these are great collectors, but these collectors all have a problem. Does anyone know what the problem is? Everyone's been talking about it for the last decade. Does anyone know what the problem with these collectors are? Yeah, they've got a big problem with pause time. Yeah. Well, they've all got big problems with pause times because in the worst case, they can cost you a lot. And this really matters in a lot of situations, right? So there was a big effort to try and address this. And a whole bunch of collectors address the question of reducing the GC pause time, starting most prominently with C4 and then also Shenandoah and ZGC. So a bunch of smart people and very good people went and worked away at how you can make GCs which had a lower pauses so as you might be able to reduce the user experience latency, okay? And but it came with a little bit of a surprise, okay? And in fact, if we look at this analysis and we analyze 2 of the collectors which are available in OpenJDK, what we see is they came with a very big performance hit, okay? But what's interesting is when we published this result, a lot of people were disbelieving. But, you know, it's all of our frameworks are available and for anyone to go and run the results again themselves. You can run this for yourself and get these same results. So the question is, why did no one notice this? I think that's the biggest question. Why did no one notice just how big this cost was? One answer to it is that many people said, oh, well, if you're worried about latency, you need a 10x heap. And if you've got a 10x heap, these things all become not so far apart in their performance. Okay, so people weren't down in this low heap size. But there's a real opportunity cost to having a 10x heap. 10x your memory doesn't come for nothing. And large companies with large data centers really care about blowing a lot of money on DRAM that they don't need to spend. So you've got this very pronounced problem that the latest collectors are actually substantially slower than the ones that came before them, which is disturbing, I think. All right, so click. Now, to your question about do we do this with something with respect to something other than time? Yes, we absolutely do. Here we go and look at cycles. The picture just gets worse. So what's happening here? We're now looking at how many cycles, not how much wall clock time, but how many cycles these consume. And you'll notice that they got the values went higher. Why do they go higher? Because they're offloading a whole bunch of work onto other idle CPUs. But there's an opportunity cost with those CPUs, particularly if you're on a phone and you're burning battery, or you're in a data center and you're burning a CPU that could have been sold to someone else to run their work on. There's a very real cost with just offloading things onto other CPUs. But unless we have metrics which expose those costs, they just get brushed under the rug. Okay, and this is getting to my point. So, and just to rub in the bad news, if you look at when these collectors were built, you can see that we've got a bit of an ugly trend going on here. And I think this is why I made the dramatic point about it being there being a real problem. And I think that this is illustrative of a real problem. And it's not a problem with that team over there or those people over here. It's a problem with the whole community, I think, and the way we're approaching stuff. And that's my point. So I'm going to give up on that clicker. It seems to be very laggy. There we go. So I think we've got a real problem here. And how did this problem happen? Well, interesting question. So I'm going to give you my take on how we got to this place. I'm going to suggest there are two fundamental reasons for this. There are probably others, and you probably have your own takes on it, which we can discuss this later if people are interested in putting forward their own theories. The first one is pretty obvious. There's a failure of measurement. And people have asked me, like, how can this even be possible? How can it possibly be that people are selling garbage collectors that are that much more expensive than they should be? And to which I just kind of shrug my shoulders and say, well, I guess they don't know it's that expensive. They haven't measured it, right? Good question. So there's a failure of measurement. We use methodologies that allow us to sweep costs under the rug. And as long as we're doing that, we're in big trouble, okay? We need to expose the cost very clearly. And if we're not exposing the cost, we're going to continue to do this. And really importantly, and this is a very underappreciated point, and I've had this discussion with people in product teams recently and repeatedly, and the point is hard for them to swallow because it's actually a really expensive one, is there is a lack of clean performant baselines. There is no semi-space in OpenJDK, okay? Why would you want semi-space? Semi-space is a really silly algorithm. Yeah, we know semi-space is a naive algorithm, but it actually serves a really important purpose. And just like Ben said in his keynote, we actually use semi-space for debugging as well as a baseline for performance. And it provides you with a really useful baseline. Same with Mark Compact. Having a Mark Compact collector in your suite is also super, super useful. But these suites don't have these things. And many production runtimes have exactly one garbage collector. And it's hardwired in there. It's not hardwired in, it's welded in there, right? It's welded in there, you can't get the thing out, and you certainly can't change it much. Right? And the other problem is lack of meaningful workloads. So we don't have workloads which are analyzing not GC pause time, which they were optimizing for, but user experience latency, which is not the same thing. And I'm going to show you that very brutally in a few minutes. There's a very big difference between reducing GC pauses and reducing user experience latency. So, second point, failure of innovation. Why have we got so little innovation? Well, Wenu, who's sitting at the back, who did a great paper before deconstructing the G1 garbage collector, and he shows how that grew and how these other collectors have all these common roots in the G1 garbage collector, which is a good thing in many ways, but it's also, there's a lot of inbreeding in the design of these collectors. They're remarkably similar. And some of the people who built them are not really aware of just how similar they are until you actually spell it out, and they kind of grudgingly sort of say, yeah, sure, okay. But I think this is a real problem too. If we're not innovative, if we're not creative, we're going to be stuck in a bad place. Why is there a lack of innovation? Weak abstraction boundaries is number one. If you've got weak abstraction boundaries, what ends up happening is that your collector gets welded in place. And once you've got a single collector welded in place, it's game over. Okay, why? Because the runtime ends up making implicit assumptions about that collector. Oh, it's got three generations. Oh, no, it's got 4 generations. It's got a write barrier that works like this. It's got a card marking barrier. The compiler can do this because the card marking barrier only does that, etc., etc., etc. Once that one GC is baked in, all levels of your runtime start, human nature says, they will start making assumptions about what that thing is doing. And once that happens, it's very, very, very hard to innovate, because you're stuck with this single point. And extracting yourself away from that point is extremely costly. The other very natural and completely reasonable one is that the production teams face imperatives about what their manager says they really need to meet next month, and they often don't have the luxury of just pontificating and designing new garbage collectors, especially if the lead time from that idea to a production garbage collector is 8 years. Forget about it. Okay, so we don't have the liberty inside the production teams to do that kind of work very often. It's very, very, very rare for people to be given that sort of scope. Okay, so that's killing us as well, and it's totally easy to see why that situation has arisen, and it's kind of quite reasonable. But the second point should be helping us there, but the third point should be helping us there, but it's not. And that is, one of the reasons why we have academia is to be taken away from the shackles that industry sometimes puts you under, and allow you to innovate and allow you to be way more creative. But if you're being creative in your own academic bubble and what you're doing doesn't transfer well to industry, forget about it. You're not solving the problem. Okay, so if you can't translate your ideas into an industrial setting, or the industry people think that your ideas won't translate into an industrial setting, then it's game over. Or if industrial people don't have the means to incorporate your ideas, any of the above are true, it's game over. We don't get to get those ideas into industry. And ultimately, that kind of is what matters. If there's a billion people running Chrome or running Android or whatever it is that's running the GC, if they're not seeing the fruits of the academic or research community, and you're not reducing the energy consumption on their phone or the CPU cycles burned by their browser, that's a real pity. So what do we do? Okay, we've got a problem to solve here. So how are we going to solve this? Fred Brooks passed away a few weeks ago. I don't know if you saw that. He was always a hero for me. I always thought Fred Brooks was a larger-than-life character in the software engineering world. And I often quote him. And one of the things I really like is this idea that conceptual integrity is so important. Right? That's been one of his things, conceptual integrity. And this is incredibly relevant to what we're talking about, VM design. How do you build a VM and maintain conceptual integrity? And I think having good abstraction boundaries is part of the deal. And yeah, I'm going to come back to that question in a bit more detail in one slide's time. So what I'm going to talk about in this talk, in the remainder of this talk, is the idea that we need modular VM development. We need, and that if we have modular VM development, and I can give you my garbage collector, and you can use it in your language, and you can use it in your language, and you can contribute to the garbage collector. It's not mine anyway; it's the community's. Then we go a long way towards this. We can share common methodologies and instrumentation. So if we develop, or when we develop, a better methodology and better instrumentation, better ways to know what the thing's doing, everyone can use it. And we can develop performance baselines. We couldn't do the semi-space collector in OpenJDK because building a whole new semi-space collector in OpenJDK would just be an enormous amount of work, like about maybe a year of work in OpenJDK. So that'd be extremely expensive. However, if we had a framework in there, a modular GC modular thing, and that thing happened to have a performance semi-space collector in there, we've got it. Okay, we already have one. So, and that helps us solve the problem that I spent the first 15 minutes talking about, that you can't measure things unless you've got good performant simple baselines. Rapid innovation. If you've got a modular VM, it's possible to do really creative stuff and have it performant very, very fast. And I'm going to make that point sharply at the end of this talk. And finally, academic research is much more easily evaluated and transferred. So if you do something really creative, the PhD student does some really cool thing. If an industrial partner has a VM which allows them just to plug in that module that they developed in the lab and evaluate it against the workloads they really care about secretly inside of their organization and say, wow, it really does solve the problem that they thought it solved in that paper they published, then it's much more exciting, because then you have the real possibility that people say, yes, we want to invest in that. We want to support your research, because we can see it on our own workloads. It's not just showing up in these benchmarks that you had in your paper, but it's something we can really see. So the ability for academic research to be translated directly into industry is a very powerful thing. Okay, so continuing the theme on abstraction from Fred Brooks, Barbara Liskov started off her Turing Award lecture with a talk about abstraction and the power of abstraction. And of course, garbage collection and memory management is a great example in the sense that you're abstracting over memory safety and you're abstracting over the way memory is managed. And she points to the power of this abstraction, of abstractions like that, and how powerful they are to us. And I think we all agree with that. But she then goes on and says, but to do this, you need to relinquish the idea that you have complete control over everything, okay? Because you don't anymore, right? And you know, when she said that, I was there. You know, when she said that, my heart sinks when I hear it again. My heart sinks. You know, I don't want to give up complete control of everything. I want to have my cake and eat it, right? I think all of us have some sense of that, at least, that you don't really want to relinquish that, and that's why I think that's human nature, and I think that's why, unless your abstractions are machine checked and machine enforced, human nature is they'll get violated, because people want to have that control over those things, right? So, and then Ben mentioned this before. One of my favorite catch cries comes from Ken Kennedy, and this came from the context of parallel computing and high performance Fortran, and he talked about abstraction without guilt, and that's what he really wanted to do. He really wanted to give these chemists and physicists a language environment in which they could have a nice abstraction with which to talk about their whatever it was they were trying to model in their chemistry or physics, and it would just somehow translate on this huge supercomputer and perform really, really well. And he wanted to have that abstraction without the guilt of the overheads associated with providing those physicists and chemists with a high level of abstraction. And that's what his life was dedicated to, is high performance Fortran and so forth. And I always thought it was a great way to put it. So, which leads me to this, because to me, that's the essence of what MMTk is all about. MMTk is all about abstraction without guilt. That's what we're trying to do. And I'm going to give you a quick digression to how I got to this place, and some of you will look at that. And, does anyone know where this is? Anyone? He knows where it is. He used to live there. Where is it, Tony?
Just around the corner from my house.
Yeah, it's in Amherst, Massachusetts. Right, so this story begins in Massachusetts when I was a postdoc. And I won't tell the whole long story, but the short version of it is this, and I think it's really super interesting. And if you catch up with me later, I can tell you the long version of the story. But basically, it was at UPSLA in 2000. Darko Stevanovic presented some really interesting GC work. But what's really interesting about it, and which some of you might find shocking, is it was all done by models of performance of the GC. Models of so here's a new GC algorithm, let's model how it performs. Why the heck would he do that, right? Why would you model the GC? Surely just run the GC, right? No, you didn't. Back then you didn't. Why not? Because you couldn't get access to the source code for the high performance JVMs, right? So Sun gave him these heap traces, and then you get these heap traces from Sun, and then run them through your model and say, oh, it's going to have this much cost in the write barrier and that much cost in the GC trace, blah, 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 blah. And his entire thesis was built on this, right? So this blows my mind to even think about this, but that's how it was back then. And at the end of his talk, someone came up to him, and I'm going to get the name wrong, so I won't even say it. Someone senior at IBM came up to Catherine McKinley, his advisor, and said, why are you using models? We've got this fantastic new JVM. And Jonathan, he was kind of on the scene at the time this all happened. We've got this fantastic new JVM, which is written in Java, and it's going to be really high performance and really scalable, and we're going to make it open source. It was too late for Darko's PhD thesis, but I happened to be the person at the time who was going to profit from this, because I was just at the beginning of my postdoc, and I ended up taking a left-hand turn. Catherine called me out from Denver and said, hey, this is so exciting. Are you interested? I said, absolutely. And then it literally changed my career. and I dived off down this rabbit hole. But that led to me working with Perry Chang and Catherine to develop this thing called the Memory Management Toolkit, which would allow us to do pluggable GCs in this thing called JIX-RVM. And the basic idea is you'd have this modular GC framework inside of JIX-RVM where people could experiment really easily with GCs. It was kind of the exact counterpoint to what poor Darko had to experience, right? And so then the abstraction without guilt thing, how does that pan out here? Good question. So what we came at was a JVM which had been built by a combination of product and research teams in IBM, and it had 3 garbage collectors in it, which had all been pretty highly tuned. They were actually written in very much in a C style, so written this kind of weird dialect of Java that was fully static. And the people who wrote it had written with very large functions and the kind of old style C type approach. What we did was completely different. We said, okay, we know who's writing this compiler, and we trust the compiler writers because we had a huge amount of respect for them. We said, they're just going to do magic. And what we're going to do is we're going to write this thing idiomatically in the best style that we can, using the best Java idioms. And we're going to they're just going to make it perform well, okay? And if they don't, we'll sit down with them and work out why and get them to fix it. And if that doesn't work, we're pretty clever, so we're going to sit down and make this particular corner case work, right? So this incredible faith in the ability of the compiler people to solve all our problems let us take a very purist view of how we code this thing. Okay, so that was the mindset from the beginning. And Perry and I were young and incredibly technically ambitious and just thought, this is going to work, no worries. And so what we did is we built this thing and then we measured it. And so we built it in Java, and we built all these design patterns into it and reused them. Had a huge amount of reuse in the thing. So the different GCs all reuse these different parts. And we had a very clear distinction between the virtual machine and the memory management part. So we built a very clean interface with the idea that this is going to be portable. That didn't really pan out in the end because JavaScript really didn't get ported to other languages. I mean, other languages didn't use that framework the way we kind of hoped, but still, we designed it so it would. And we had this composition with low-level mechanisms like write barriers or whatever it might be. Then we had this idea of policies, which are things like semi-space or IMIX or mark sweep. And then we had plans which combine these things together, the idea of composition of these things. And we managed to write this thing up, and by some miracle, ICSI accepted the paper, and the results were really interesting. So what you see here is the Watson means the ones that ship with from the IBM research team, and the 2.0 was the first one we started with, and 2.2 was the improved one after they got our results back. And here you're seeing a bunch of different software engineering sort of metrics on the code complexity. And you can all disagree about whether these are remotely useful, but the bottom line is we improved it. By any measure you chose, we significantly improved or lowered the complexity of the code base, okay? So we've greatly lowered the complexity of the code base, so now you can build things much more simply because there are way more composition, way more modularity in the software. So that's great. So we win on the software engineering front very clearly, which is terrific. But what about performance? Well, turns out we did really well on performance too. So I've just cut this straight out of the paper, so apologies for the black and white picture. But what you see here is if you see the squares, that's one collector, and you see the circles, that's the other collector, and you can see the movement is actually quite substantial on the same sort of graph as I was showing at the start of the talk, with space on the x-axis and time on the y-axis. So what we managed to do here is we both greatly simplified the code, made it easier to work with, made it modular, and we improved performance, okay, for the same family of collectors. So we're trying to make the same collectors. This is not like we put new collectors in. These are the same collectors. So I counted that as a real win, and Perry and I felt very vindicated in our slightly wild and crazy, ambitious approach. So what was the successes from here? Well, it was a clear example of the power of software engineering. If you take it really seriously and have a lot of faith in your amazing colleagues who are building the compilers, then you can go a long way. And one of the outcomes was, as Tony said in the intro, this was used for a lot of GC work in the subsequent decade or so. So I think undeniably it was a success in that level, but there were also the downsides. So first of all, it was tied to JavaScript, which had a finite shelf life, and when it sort of slowly faded, so did the fortunes of MMTk. But it also, and perhaps the most important thing, was that of all the innovation and wonderful things that went on in the MMTk project, almost none of it made its way into industry. And I found this very disheartening. And I've already sketched for you about 10 minutes ago some of the reasons why that might have been the case. But nonetheless, it was very, very disappointing. And also it was very Java-centric. And we know there are many languages in the world other than Java which need good GCs. So I was very compelled to think about where we could go next. And could we build a framework that would go beyond this old one? And indeed, that's exactly what we've done with MMTk 2.0. And we kicked it off with a paper where we did something very, very simple, not building a framework, but just seeing if we could build a garbage collector in Rust and seeing how well it would perform. So we did this experiment E. Lin, who'll be here later this week for anyone who wants to catch up with him. E. Lin was the lead author on this paper. And what we did is we found that we could actually build this garbage collector and have it outperform. We built parallel garbage collectors in C++ and in Rust, and found that the Rust one performed very, very well. And most importantly, there was very little unsafe code in there. Okay, so by and large, a lot of the code was actually just straight natural Rust, and the amount of unsafe code was quite minimal. When you gets more and more close to the metal with a large VM like OpenJDK, the amount of unsafety may grow a little bit, as I can see my students whispering in the back about, well, it's not quite so tiny amount of unsafe code there now, but we did find that we could isolate it really well. So what are our motivations here? So if you're an industry, you can think that if you had a framework like MMTk that worked with your VM, then there's an opportunity to engage with the research community, because someone could come up with a great idea that they may have evaluated in OpenJDK. Maybe you can then translate that into your VM, which is Ruby, right? So there's a good opportunity here now to engage with the research community, which for a long time I think was overly dominated by Java. So the Java industry people engaged with the research community somewhat, and most of the other people didn't really engage that much with the research community. Generalization, but broadly true, I think. And it also means, as I said before, industry can now evaluate things on their own terms. So if you had a framework that you could plug into your production VM, you may have proprietary workloads, or you may have user traffic you want to evaluate against, or mirrored user traffic, and see how does it hold up there. It looks great in the paper, but let's see how it holds up here. You can do that if it just plugs in, right? So this is a very, very attractive from the point of view, from the industry point of view. From the academic point of view, it means you've got this. The flip side is you've got an industrially credible framework in which you can do your research. You've got greater visibility because you've got more languages now that you're exposed to. And it allows you to do rapid and performant development. So you can build things quickly that perform well. So what's the design approach? It borrows on the original MMTk, and it looks something like this. So what we have is a VM interface, which, we have two broad components. You've got your VM on the left there, which in this example is OpenJDK. And on the right, you've got the memory management toolkit. And everything on the right is purely in Rust, and it's 100% VM agnostic. So it knows nothing about any particular runtime. And by contrast, everything in that box on the left knows nothing about MMTk. Okay, so these two boxes on the left and the right know nothing about each other whatsoever. And all of the knowledge that's shared between them fits in these thin layers, which we call bindings. Okay, and we have a VM interface in which we write OpenJDK specific code for MMTk. So MMTk needs to do things that are runtime specific, like find all the pointers in an object. Okay, and we can do that in this that brown box at the top center. And conversely, OpenJDK needs to do things like please allocate an object or do a write barrier. It needs to do those things on behalf of MMTk, and it's probably going to want to do those in C++, and that's what's happening in that white box at the bottom. Okay, and then we can replicate this out for multiple VMs, which is exactly what we've done. So, and the idea there being that these white boxes on the left are quite independent, as I said, of MMTk, and MMTk doesn't have to change as all these other VMs come along. So what's our current status? We've got performant ports to OpenJDK and JXR VM. By performant, meaning that it performs as well as we could expect, meaning that it performs as well as the production GCs, even better. Okay, Julia is on the cusp of that. It's meaning that Julia is already outperforming the Julia native GC on certain workloads. We haven't got to the point where we're doing it across the board, but it's already doing. Yep.
What about the stability and quality?
Yep. That obviously it's MMTk at the moment is not going to have the stability and quality of the G1 collector, which has been built over 15 years. But so it's a question of how long it takes to get to that point. I'm going to get to that in a minute, but it's going very well. And one of the big advantages is as you've got more runtimes on there and you've got a focused kernel where all the activity is, you can focus your efforts on getting the stability and quality of the core parts of the runtime. So I think actually it's a lot more. If you've got 3 or 4 monolithic garbage collectors, it's far harder to maintain stability and robustness across those 4 completely independent collectors than if you have a framework on which the kernels are very heavily tested by all these collectors. So that's part of the design philosophy, which I think we've got to be. Yep.
And I think there's also like the performance and stability of the GC implementations themselves and also of the bindings.
Sure.
And maybe you can also like shed some light on how the bindings, for example.
Sure. I'm about to get there. So Julia is on the cusp of this. We're working with the Julia people very closely, and likewise with Ruby. Ruby's not quite got to the point where we're doing performance testing. We're still doing robustness testing. And you might think, how long does it take to do this anyway? I mean, how long building a binding? Sure, that's a few weeks maybe. And then there's PyPy, and then there's Haskell, which we've really only just gotten started with, but it's a lot of work there. But so what are the highlights? So we've got a strictly runtime neutral core. I've emphasized that. We've got abstraction integrity enforced by the compiler, and this is very important. Okay, so as I said before, human nature is for abstraction leakage to occur, but if it's enforced by the compiler and the linker, then you can and your continuous integration, then you've got defenses against abstraction leakage. One of the important points is the work packet scheduler, which is a key design difference between the new MMTk and the old one. And when you show at the back there implemented this, and the basic idea is you've got these work packets, which are small kernels that do the vast bulk of all the GC work, like the inner part of the tracing loop. And they're modular in an object-oriented style. So I give you a work packet, and what that has is the semantics for processing each work item and a big list of work items. And as a worker, you just keep grabbing these things off of work queues, and you process them in an oblivious way. So each worker, GC worker, just grabs work items off work packets of work queues, processes the items, and then goes and grabs another one, which could be a different functionality for a different GC, for whatever. So what it's doing is it's capturing the work in a very succinct way, in a very rigorous way, and those kernels are often just tens of lines of code. Okay, these little kernels of what you do for each pointer that you come across. Here's the code. And so the GC threads simply crunch those. Then you have a scheduler which schedules the GC threads. And you've got predicates that say this work can happen only after that work is completed. So as a GC designer, your job is to write these kernels. If you have to write new ones, you may not have to, because you could maybe reuse ones that have already been written that do what you need, and define the predicates. So this thing can fire after that work's completed. So you can't start moving objects until the roots have been traced, or things like that. And interestingly enough, one of the side effects of this and limiting it to these little kernels, or focusing in on these little kernels, which is where most of the activity happens, is it's amenable to verification. Formal verification is a long way off, but we have made progress here, and we just published this paper only a few weeks ago, a couple of months ago, led by a group from UMass, where we're looking at model checking, but the model checking is focused only on these little work packets. Okay, so model checking is one of these vast, complex GCs is a big ask, but model checking these kernels is totally practical, and that's what we're doing here. So, sorry, click through this, and we get the performance and safety of Rust. We're not using any C++ code if we can avoid it, and so it's all in Rust, and that has its own benefits. And it's open and liberally licensed, so VMs can feel happy about binding with it. So I'm just going to quickly go through some case studies. The first one is the OpenJDK binding. When you implemented this, he's sitting in the back there. So we're looking at a very mature, highly tuned, and very complex runtime. That's OpenJDK. We're very fortunate because JEP 304 did a massive refactoring and GC isolation right before we started our work. And that literally saved us years of work. And the amount of work it took them to do it was absolutely enormous. This is a very big refactoring of OpenJDK, and the basic idea was to isolate the different garbage collectors so that they can implement new ones. So we're very, very fortunate this had happened, and it took them a year and a half to do this, and that was a lot of very capable people from Oracle and from Red Hat working on this project. So I'm highlighting this point to help you understand that when you do a port to MMTk, this is the first job you're going to do, is you have to clean up your own runtime. And that can, in the case of OpenJDK, it may be 18 months of a handful of people who are very, very close to the code working on it, both at Oracle and Red Hat. In the case of something like Julia or Ruby, we've been working on Julia for about a year now, and we've been working on Ruby for about a year now, very closely with the core implementers. And it's a year's worth of work to refactor and clean out these abstractions without any performance loss, because they won't tolerate any performance loss. So cleaning out these abstractions so we can put MMTk there for a monolithic VM which has never done this before, it's a lot of work. Okay, but the payoff for them is huge, whether or not they use MMTk. Like the OpenJDK people, they did it even despite MMTk. It meant they could build ZGC, or they can integrate ZGC, and that was what motivated this piece of work in particular. So there's a big payoff for them. So I'm going to give you an example here of object scanning, and this is an example, and so this is coming, I think, to one of the questions you asked before. This is performance critical GC code, which is runtime specific. So this sits in the binding, but we want it to sit in the Rust part of the binding because we want this to be really, really close to the heart of MMTk core, but it's reflecting the semantics and the organization of OpenJDK. So ultimately what we end up having to do is port the key code, which in this case is scanning an object instance. We port it to Rust. And you can see here, that's literally the code out of GitHub, which I snapshotted last night. And you can see that's the original code, and this is our Rust implementation. And there are a few places like this where it's essential for performance to avoid language crossing on every single object scan to replicate that code. And the same here for the case where you've got an array of pointers. And then conversely, so that was a case where MMTk really needed knowledge about OpenJDK. Okay, so that was then porting the C++ code to Rust. And this is the converse. This is the case where we've got the Rust implementation, and now we've got to lift it into OpenJDK. And this is the field barrier, which is a write barrier that we use in some of our collectors. So it's a very simple but elegant write barrier, which hopefully won't take very many instructions to execute, but actually implementing it in a really advanced compiler is a lot of work. And so that's how it looks inside of the interpreter. So this is lifting code that's written in Rust in MMTk, lifting it into the OpenJDK interpreter. That's lifting into C1, and that's lifting it into C2. Okay, so that's a non-trivial amount of work, but you only need to do this once or twice for these absolutely performance critical parts of the GC, both on the GC side and on the runtime side. Yep.
And those also like to come out of sync with OpenJDK?
You've got to maintain it, but fortunately the write barriers tend not to change very fast, as you probably know if you know the OpenJDK's code base. It doesn't change very fast. So, but you do have to. That is a point, but there's only a few things that you need to do that. The allocation sequence and the write barriers are basically it, and they're very, very stable. But you obviously have to track them. Okay, so Julia, it's a very high performance runtime, carefully crafted high performance mark sweep garbage collector. They've got exactly one, but that one collector was very carefully welded in. Okay, so we had to unweld it, which is a lot of work. It was a single file with 4,000 lines of C code. The tracing loop itself was 700 lines of code with go-to statements and all sorts of exotic stuff there, and it went really, really fast. But we had to unpack all that and then put in an abstraction layer, which we've done now. It's got an LLVM code gem with a shadow stack, which we had to understand. It wasn't documented as a shadow stack, but we figured that out. We worked with the people, with the key developers. So we did eventually work all these things out. But most importantly, in the case of Julia, there's very strong implicit assumptions that objects will not move. Okay, that's an implicit assumption throughout the code base, because the original collector was one collector, it was a mark sweep collector, and it did not move objects as it happened. So then assumptions went everywhere that things won't move. So then a large part of the project that we're working on right now is finding out the places where things actually, we want to be able to move things and where we can move things, because it turns out there are lots of opportunities to move things, but the default assumption is you can't do it anywhere. So we have to work out where you can do this safely, and doing that with the people who wrote the code originally to make that clear. And one of the other ugly things is their native code interface, unlike the Java native code interface, is very liberal and lets the native code do pretty much whatever it likes, which means that they can transitively traverse an object graph without telling you. So anything that is referenced by native code, at least in the current version of Julia, you have to transitively pin everything reachable from anything that is natively reachable. So that's a bit scary. What were the major tasks for us? We've spent more than a year on this. Tony's my partner in crime, Eduardo, has been the lead on this. We spent more than a year on this. We had to introduce a strong GC abstraction layer. We had to codify the semantics with respect to object movement, which were not explicit at all. They're just implicit semantics. And we had to unpick the existing GC, which is quite. Tony and I spent a lot of time with Eduardo trying to understand what that was doing. The last case study I'll talk about is Ruby. It's a very well-established VM. It's got a very unusual GC, and the runtime doesn't enumerate reference to native objects. If you have a native struct, you write your own code to tell the GC what to do with it, which is kind of weird, and it has very strong assumptions that things won't move. So if you write a thing called foo here, you also write a thing called foo mark and foo compact, and that is the Ruby user writes this stuff. But this makes life rather complicated for the GC because it's got a rather exotic approach to how you do GC, and it's got some other exotic things like the basic GC only has 40-byte objects. If you want anything bigger than 40 bytes, that's fine, but what it does is it mallocs the other part, and then, anyway, it's very, very exotic, and it's quite mature, so it's a lot of welded-in assumptions about all kinds of stuff. All right, so we spent all that time thinking and building stuff, so how does this actually perform? And I'm running out of time here because I've been too loquacious. So this is a paper we published at PLDI, and this is the one that answers some of these problems. And going back to those graphs I showed you before, what's the problem with the current high performance, the low pause collectors? Well, the first thing is they target pause times. They don't target latency, they target pause times. And that in itself is a deep problem because user experience latency is not purely about pause times. If you reduce throughput and you're in a real world system with a queue, work gets backed up and you introduce large latencies just by virtue of the fact that you're not getting through the work fast enough. They depend entirely on tracing, which means in the limit, you have to trace the entire heap before you find that something's dead. And they depend entirely on evacuation, which means that you cannot reclaim space unless everything in that space is dead or moved out, which means you have to move things out. And they depend on expensive read barriers. So they use quite expensive read barriers to do all this stuff. LXR, which is developed by WinU at the back there, instead of targeting GC pauses, it targets user-observed latency. And that sounds like a nuance, but it's a big difference. It uses high-performance reference counting, so it doesn't use tracing. Well, it does use tracing as a backup, but it's not. Its primary collection mode is high-performance reference counting, which means it has a much greater immediacy, so it collects things very quickly. And it uses opportunistic copying, which means it moves things when things are easy to move, when it's convenient. If it's not convenient, no worries, just leave them right where they are. Okay, and that is enormously powerful. For one thing, it means we do not need to do concurrent copying because we don't need to evacuate everything to be able to reclaim space, which means we don't need to put everything, and if you evacuate everything, you have to do concurrent copying because you can't possibly do it in the pause, otherwise you have huge pauses, which can give you big latency. So we avoid all that by opportunistic copying, which gets us out of jail with respect to concurrent copying. What's the results? This is one result out of many from the paper, and this just shows here the latency. The green curve at the bottom is LXR. So what you're seeing here is compared to G1, Shenandoah, and ZGC, we're getting much better latency curve, and we have 3 other latency critical benchmarks where we see similar results. So we're absolutely nailing it on latency. The summary result in a tight heap, there's G1, its latency, and LXR's latency here is substantially lower than it is. ZGC in the really tight heap won't actually run because in this version of OpenJDK it wouldn't even run in a big heap. Then when you make the heap bigger, we've still got a substantial lead. Oh, and the important thing is we're also winning on throughput as well as latency, and that's the important insight. Okay, so we're winning on throughput and latency, and we're running better in a tight heap. Okay, so you see this graph here, finally. That's how all the other collectors perform on JDK 11 when the baseline includes something like semi-space, unlike no GC, and you can see they've got substantial cost, and there's the elbow for LXR. So LXR has better, lower cost than all these other collectors, and yet has substantially better latency. So we're winning on all fronts. Now, and the same is true on cycles, even more so when you measure cycles rather than wall clock time. This is the punchline, and this is what I really want to emphasize here, is that LXR did all, WinU did all the work on LXR to get to the point of a PLDI publication in just 19 weeks. Okay, that wouldn't have been possible if we didn't have the MMTk framework, we didn't have an EMX garbage collector in there, we didn't have high performance write barriers already in there, and all these other things there. But because those things were already there, just implementing the LXR algorithm, which is quite an exotic algorithm and non-trivial, and you can see it's outperforming the production collectors there. Doing that, I think, is remarkable in a 19-week period, and I think that's entirely because we had a modular framework, high-performance, highly tuned framework on which to build. So that's kind of more or less the punchline. So to summarize the talk, we've got a real problem in the GC community broadly, I think. Abstraction is the key, I think, and our design approach allows us to work with multiple languages at very, very low cost, or extremely low cost. And I just want to emphasize the fact that we could build a entirely new garbage collector, which has very interesting properties, which outperforms these really well-established production ones that are built by large teams, and we can do it in 19 weeks. And that work is now being productized. So it's a very serious garbage collector. So, and that's it. Thanks.
Question: do we have a mic? Is there a mic that we're using?
think I can take this off and use the other mic now.
So for the bindings to those various VMs,
Yep.
A lot of it is like generating compiler IR. What if you generated something in between and then generated the thing that generates compiler
Yeah,
IR?
great question. That'd be a really interesting project, but that would also apply to their existing barriers, right? So people have written those by hand. Whether or not you could lift that and then generate them automatically, that'd be a really awesome thing to be able to do if you could. I have no idea. You're the compiler guy. Great question, though.
Yeah, so VMs have all these weird features like interior pointers, pinned objects, finalizers, weak references, blah, blah, blah. So you have to support like the union of all those features in MTK. And because it seems like they interact poorly in general, right?
No, I mean, great question, but they don't necessarily need to, right? So, for example, pinning. If you require pinning, well then, sorry, you can't have semi-space. It simply that algorithm simply doesn't work if you've got pinning or mark compact, right? So once you declare as a runtime that you've got these constraints, then the collectors you can use become naturally limited. So that's why it's not as bad as you might think, because in fact we don't need to sacrifice everything to achieve pinning. We're not going to say, oh, everyone has to have algorithms that can support pinning because one of our clients wants pinning. No, we offer the other ones, and we just the client that wants pinning has to live with that. In terms of reference types, yeah, we've moved to a point now where we've got the core infrastructure for different reference point, weak pointers and whatnot in the core, but all of the semantics are lifted to the binding because they're so exotic, and some of them have some pretty weird ones, like in Ruby and Ruby in particular has some pretty interesting ones, semantics. And so be able to support all those things, basically they get lifted to the binding. And if they're really weird, well, the binding becomes weird, but that's a function of the language.
Yeah, thanks for the talk. Quick question. So LXR is, you said it was highly performant, but you're using your elbow metric, which is a lower bound. How is it truly highly performant if you look at other types of things like, doing geometric mean runtimes across benchmarks?
Oh, absolutely. And we present those results in the paper. So we look at the geometric mean of the performance. I just use the same methodology because it's useful to see how much it costs in total. And those graphs there will show you, the graphs I showed you, they map. If you look at the geometric means of the performance results in the paper, which there's a lot of data in the paper, you'll see that they're completely consistent with what you saw in the graphs because it's ultimately the same data. You're just subtracting a baseline out of that bottom line. You've got a bottom line that you're plotting with the geometric mean of, and in those graphs there, you're subtracting a baseline out. So really, I think all you're doing is placing the zero axis at a different point. That's essentially, in a nutshell, what you're doing here is you're just moving this axis to reflect where the zero cost is.
Any other questions? All right, thank you, Steve.